Having wrapped up our applications of differentiation to graphing, some more applications. We're going to go back and look at limits and use derivatives to help evaluate certain limits. So 4.5, indeterminate forms and L'Hopital's rule. So quick return to limits. We'll use derivatives to evaluate limits of a particular form, and we'll be specific about that. This technique is called L'Hopital's rule, and according to our textbook, the result is originally due to Johann Bernoulli, but was first published by Guillaume Francois de L'Hopital in the first Introduction to Differential Calculus textbook. So I guess that's monumental. Here's Bernoulli and L'Hopital. Appear to have the same hairstylist, I suppose. These are two different people, though the images look the same, and they lived at the same time. These images are from the Mac Tudor History of Mathematics Archive, FYI. But we want to get into applying this rule to simplify taking limits. A bunch of the limits we initially saw back in chapter 2, especially early on, we solved them by factor, cancel, substitute. Factoring is algebra, canceling was justified in the limit setting, and the substitution was the tricky part, was justified for polynomials and certain kind of rational functions and trig functions at certain places in the domains of those functions. What had stopped us from just substituting in the beginning was very often the numerator and the denominator both had limits of 0. So we couldn't just substitute in, we'd get division by 0. But that was a pattern. Oftentimes when we had 0 in the denominator, we also had a 0 in the numerator. You know, that's why the cancellation allowed you to substitute at a later stage on those kinds. So those kinds of limits will be dealt with using L'Hopital's rule. A definition, we're defining a form of limit, just to give it context. The limit as x approaches a of f of x divided by g of x is in the 0 over 0 indeterminate form if the limit as x approaches a of f of x equals the limit as x approaches a of g of x also equals 0. So if the numerators and denominators both have limits of 0, then this is a limit of the 0 over 0 indeterminate form. The limit is of the infinity over infinity indeterminate form if the limit of the numerator is plus or minus infinity and the limit of the denominator is plus or minus infinity. So both numerator and denominator go to infinity in a limit. Beware, okay, this is not an arithmetic notation. This is notation describing a kind of limit. I'm not saying 0 divided by 0. I'm not doing division with an infinity symbol because, as you know, that's meaningless. So that couldn't mean arithmetic things. What we're using those symbols for is to describe particular types of limits, limits as described. It's L'Hopital's rule that allows us sometimes to evaluate indeterminate forms of these kinds of limits, and we've encountered both of these kinds of limits, indeterminate forms of the types defined in previous sections. We'll give a proof of L'Hopital's rule at the end of the section. Let's state some versions of it first and illustrate those. Okay, first, for the 0 over 0 indeterminate form of a limit, we have the following version of L'Hopital's rule. Suppose f of a and g of a are both 0, that f and g are differentiable on an open interval, I containing a, and that the derivative of g is non-zero on I except possibly at a. Here we are requiring the function be defined at a, but we're not requiring anything of the derivative at x equals a. in terms of a value. We are requiring differentiability, but we're requiring a non-zero derivative except possibly at a. Then the limit as x approaches a of f of x over g of x equals f prime of a over g prime of a, assuming the limit on the right side of the equation exists. Assuming limit exists, we'll get this value for it. So if we have a 0 over 0 indeterminate form, which is what this sets up, then what we can do is not take the limit of the functions, but take, in some sense, a limit of the quotient of the derivatives. Nothing to do with the quotient rule. It means what it says. It says the limit of this quotient is the quotient of the derivatives evaluated at x equals a. So yes, it deals with derivatives. Yes, it deals with quotients, but it doesn't deal with derivatives of quotients. It deals with a quotient of derivatives, which is a totally different thing, because the quotient rule for differentiation is somewhat involved. L'Hopital's rule, it holds for one-sided limits as well. What we're going to do notationally, and you will do this when working test problems, is we'll put the indeterminate form over the equal side whenever we use L'Hopital's rule. So if I've got a 0 over 0 indeterminate form, when I apply L'Hopital's rule, as stated there, I'll put little 0 over 0s over the equal signs. That accomplishes two things. It indicates to, quote unquote, the reader that we've used L'Hopital's rule, because it won't always be very clear how those two limits are related, or the limit value is related to the limit itself, unless you get some indication that you've used L'Hopital's rule. So this accomplishes that, communicates the fact that you've used L'Hopital's rule, and you make sure you check. Make sure we've checked that the limit actually is in an appropriate indeterminate form so that we can apply L'Hopital's rule. Don't get in a habit of just willy-nilly applying L'Hopital's rule because it came with a setting. It came with some hypotheses. Okay, these limits are familiar. Let's show the limit as x approaches 0 of sine x over x equals 1. We showed that back in chapter 2, I think it was, originally. And the limit as x approaches 0 of 1 minus cosine x over x. And we had that limit was 0 back in the day. Actually, we had the negative of that, but the negative of the limit is negative 0. And we'll indicate, as mentioned, that we've used L'Hopital's rule with this notation I wish to introduce. Okay, so when we established these limits back in chapter 2, it was quite the chore, and we used the sandwich theorem. This is a whole bunch easier. All right. With f of x equals sine x and g of x equals x, in this first one, we have the quotient f of x over g of x, limit as x approaches 0. So take a to equal 0. Indeed, we have f of a and g of a equal to 0. So this really is a 0 over 0 indeterminate form. The hypotheses of L'Hopital's rule are satisfied. So the limit as x approaches a of f of x over g of x, here, just converting it into the question asked, f is a sine function, g of x is just the x function, a is 0. It becomes this. This is of a 0 over 0 indeterminate form. We couldn't factor, cancel, substitute back when. That's why we had to use the triangle inequality. And we didn't know this thing here. This was before we had even done derivatives. 0 over 0 indeterminate form. Well, L'Hopital's rule says, then we'll take the derivative evaluated at a of f and the derivative of g, the denominator, evaluated at a. F of x is sine x, so f prime of x is cosine x. Excuse me. So we'll have the cosine evaluated at a, and a was 0. G prime of x is 1, so g prime of a is also 1. So what we get upon applying L'Hopital's rule, there you go, equal sign with the indeterminate form over it to indicate we've used L'Hopital's rule. So that's where this comes from. Converting it into the symbols we have here, the sines and cosines and so forth, gives us cosine 0 over 1. Cosine of 0 is 1. That limit's 1. Yeah, you already knew that limit was 1. We did it before. Before, we drug out the sandwich theorem. We looked at some figures. We compared areas of sectors to areas of triangles, if memory serves. It took a little while to do. Well, this is a whole bunch easier. How about the limit of, as x approaches 0, 1 minus cosine x over x? Of course, that limit was 0. As we saw, these were two fundamental limits concerning sines and cosines from sometime in chapter 2. Okay, we'll assign names to these functions. We'll see x approaches 0. That numerator approaches 1 minus the cosine of zeros. Yeah, that's 0. Cosine of 0 is 1. So the numerator approaches 0, so does the denominator. So this is indeed of a 0 over 0 indeterminate form. So we'll take derivatives of these two functions and plug 0 in. Derivative of 1 minus cosine x. See, derivative of a cosine is negative sine, so we'll have negative sine x. The negatives are gone, the 1's differentiated away. Derivative of x is 1, and we'll plug in that value a, which is 0 in this case. Both of these x approach 0. Sine of 0 is 0. We get 0 over 1. I'm just checking, making sure we don't get 0 in the denominator. Had we tried to substitute in earlier, we would have. That's why we couldn't substitute in earlier. We get 0 over 1, no problem. That's 0, and that limit is 0. So let's just start with those. And there's an illustration of L'Hopital's rule. And hey, there's the easy way to remember what the values of these two limits are. To the notes. Let's do a couple more examples. Okay. By the way, why didn't we do these limits this way in chapter 2? Why don't we just use L'Hopital's rule then? And what do we use these limits for? Why are we so fascinated with these two limits for trig functions? First off, in chapter 2, we hadn't differentiated. So we couldn't use L'Hopital's rule because we didn't know how to differentiate. And that's a topic from chapter 3. Secondly, that's what we use these limits for, was to figure out how to differentiate sine and cosine. So the whole reason for not doing these earlier was the fact that, well, you didn't know how to differentiate these earlier. In fact, you use these to figure out how to differentiate sines and cosines. So this is a good way, L'Hopital's rule is a good way to remember the values of these two limits, but we did them in the order we did them because we had to, for it to make sense. No circular reasoning. Another standard L'Hopital's rule question. Evaluate this limit, indicate the indeterminate form. X approaches 0, that denominator certainly approaches 0, that numerator approaches sine 0 minus 0, 0. It's a 0 over 0 indeterminate form. So we can introduce functions representing the numerator and the denominator. Need to do that to find their derivatives, really. Derivative of the numerator is cosine x minus 1, right? Derivative of the denominator is 3x squared, right? So let's try to apply L'Hopital's rule. Problem is, it doesn't work in one application of L'Hopital's rule. So we're adding up new things that can happen. Limit as x approaches 0, sine x minus x over x cubed. Yeah, 0 over 0 indeterminate form. Okay, well, let's take a derivative of the numerator and the denominator, and that produces this, which is also of a 0 over 0 indeterminate form. Okay, well, then let's apply L'Hopital's rule again. Derivative of cosine x minus 1 would be negative sine x minus 0. Derivative of 3x squared would be 6x. How about that limit? Oh, that's still a 0 over 0 indeterminate form. In fact, pieces of it look familiar. I see a sine x over x somewhere in there. Well, let's apply L'Hopital's rule. a third time. We did it 3 times, right. I see the indeterminate form over the equal sign every time we use L'Hopital's rule. So I can backtrack and see how many times we use L'Hopital's rule. Differentiate again. It's just going to go on forever. Well, the numerator is going to start flip-flopping between sines and cosines. The denominator eventually will become a constant if we differentiate it enough. So this has to terminate at some point. Do it again. Derivative of sine is cosine. So we get a numerator here. The derivative of negative sine is negative cosine x. The derivative of 6x is 6. And don't do the L'Hopital's rule thing again, because this is not of an indeterminate 0 over 0 form, or the other form for that matter. X approaches 0. That cosine function is continuous. We can substitute the 0 in. We get negative cosine 0 over 6. Cosine of 0 is 1. The answer is 1/6. So what we did was apply L'Hopital's rule. That created a new limit. How do you do that new limit? Well, it's still of the 0 over 0 indeterminate form. So apply L'Hopital's rule again. Gives you new limit, still of the 0 over 0 indeterminate form. Apply L'Hopital's rule again, and you get the value. So you can use L'Hopital's rule repeatedly like this. It doesn't always happen in a single step. In fact, these are more interesting, I think. But the previous example, we were able just to, in one application of L'Hopital's rule, get an answer out. Another one, excuse me briefly, I wanted to do 2 of these. Yeah, let's do this one as well. Okay, another limit says use L'Hopital's rule to evaluate. It's a one-sided limit, so that's new. It's got logs in it. Log x minus log sine x. All right, what you gonna do with that? For one thing, it ain't a quotient. So I got no chance of getting this 0 over 0 or infinity over infinity because there is no over. There's no division in it. But I can do something about that. Let's rewrite the difference. Log x minus log sine x is a log of x divided by sine x. Properties of logarithms: when subtracting logarithms, the difference of the logs is the log of the quotient. That's how we verbally express that. So the thing of which we're dealing in terms of a limit is equivalent to this. So we can rewrite the given limit as x approaches 0 as a limit as x approaches 0 from the positive side of this. That's got a quotient in it. Okay, it's got a log function in it too. But wait a second. Log functions are continuous everywhere. So assuming this limit inside exists, and it's in the domain of that log function, I can take limits in and out of that log function. No problem, log function's continuous. Now this comes contingent on us not getting the log of 0 or the log of a negative. So this thing inside, I need that limit to exist, and I need it to be positive, and it will be. But I can take limits in and out of continuous functions. That was the very definition of continuity. Now we're looking at here a limit where numerator goes to 0 and denominator goes to 0. It's a 0 over 0 indeterminate form of that limit. And that limit's inside a log function, but more of that shortly. Okay, so we'll apply L'Hopital's rule to the limit. Even though it's one-sided, L'Hopital's rule is still valid. Derivative of the numerator, x, is 1. Derivative of the denominator, sine x. Derivative is cosine x. Now we've got a limit as x approaches 0 from the positive side. 1 over cosine x. Can you substitute in? Sure. Cosine function is continuous at 0, as long as we don't get division by 0, and some concerns about that log function. What happens at 0? Cosine of 0 is 1. Okay, we can divide by 1. We got 1 over 1, so we got the natural log of 1. Remember, I was worried about this limit being in the domain of the log function. It is. It's 1. If it were 0, I'd have concerns. I'd have a problem. If it was 0 and if it was negative, I would have a problem. It's 1, so we're good, and the natural log of 1 is 0, so that must be the limit. So what we've done is taken L'Hopital's rule and combined it with some other stuff. Log functions and an idea of continuity. L'Hopital's rule can be applied to infinity over infinity indeterminate forms. We'll illustrate that here shortly as well. We can use reciprocals to rewrite an infinity over infinity indeterminate form as a 0 over 0 indeterminate form. I didn't just say 1 over 0 is infinity and 1 over infinity is 0 because that doesn't make sense. Here I didn't say 0 divided by 0. I called it the 0 over 0 indeterminate form. It's a form of a limit. It's not a number. So it's been given specific meaning. But using reciprocals in limits, sometimes I can interchange the infinite limits with 0 limits using reciprocals, and that shouldn't be a surprise to you. Our textbook says, more advanced treatments of calculus prove that L'Hopital's rule applies to the indeterminate form, infinity over infinity. All right, so we won't have a proof of this, though if you're into that kind of thing. Here's a link to some notes that'll include a proof. This is from a senior level analysis 1 class. So if you're in math, this lies in your future. But for now, we'll just take this as given. And it says roughly the same thing. Let me paraphrase. If the numerator and the denominator in a quotient each have limits of infinity or negative infinity, so the numerator, f of x, has a limit that's infinite, positive or negative. The g of x function has a limit that's infinite, positive or negative. And I have some concerns about differentiability, and I still have concerns about division by 0. Then the limit as x approaches a of f of x over g of x is the same as the limit as x approaches a of f prime of x over g prime of x, assuming that limit exists. Well, that's the same thing we did before. Limit of the quotient was a limit of the quotient of the derivatives. That's L'Hopital's rule when dealing with an appropriate indeterminate form. In this case, infinity over infinity indeterminate forms. So the technique will be similar to what we just had. Comment about these also holds for one-sided limits. These also hold when x approaches plus or minus infinity. The x value approaches plus or minus infinity as well. And some of these examples will involve that. Let's look at number 46. Number 46 says, evaluate this limit. Limit as x approaches infinity, there's a equals infinity, of x squared times e to the negative x. Write the indeterminate form over the equal signs like we've been doing. Okay, so we'll take f of x to be e to the negative x and g of x to be the x squared part. All right, you know, I don't have a quotient, so I won't have any of this infinity over infinity stuff, but maybe I can change it into that. So we've got the limit as x approaches infinity of g of x, the squaring function. Of course, that goes to infinity. Limit as x approaches 0 of the e to the negative x function. That goes to 0. There's an example from a couple of chapters back where you establish that the limit as x approaches negative infinity of e to the x equals 0. The exponential function has a horizontal asymptote of 0. And this you're familiar with from your past experience. Horizontal asymptote over to the left side, to the right side, it grows exponentially fast. It's an exponential. So if we look at this limit, I would say this is of, what is it? One of them went to 0 and the other one went to infinity in a limit. So I call this a 0 times infinity indeterminate form. All right, well, we hadn't discussed those yet. We will soon. And this hasn't formally been defined, but that's what I'm thinking. Here's a way not to think. Well, what is 0 times infinity? No, you don't do arithmetic with the infinity symbol. So this doesn't make any sense to perform that as an arithmetic operation. Got it? That's not what we're doing. We're dealing with a limit. So I want to evaluate this limit. And my problem is, it ain't the right kind of indeterminate form to use L'Hopital's rule. But wait, let's rewrite it in a different form. Let's write as a quotient, and then we got a chance at some L'Hopital's rule stuff. Okay, So let's take that e to the negative x and move it to the denominator as an e to the positive x. So x squared e to the negative x, let's rewrite that as the equal expression x squared divided by e to the x. Hey, now the numerator goes to infinity, so does the denominator. This one's in an infinity over infinity indeterminate form. So what we've done is change the original form of the function into something different. It's kind of like what we did with a log function. Different rules here, but we're writing the function in a different form, and it's a more convenient form because we can use L'Hopital's rule on this one. So we'll take the limit of x squared e to the negative x, rewrite it as a limit as x approaches infinity, x squared divided by e to the x. Numerator goes to infinity, so does the denominator. It's of an infinity over infinity indeterminate form, so we can apply L'Hopital's rule. Some concerns about the derivative. These are nice differentiable functions. In the denominator, we're not going to have any zeros pop up. So let's see. L'Hopital's rule would say differentiate the numerator. Okay, derivative of x squared is 2x. Differentiate the denominator. Derivative of e to the x is just e to the x. And it's still in an infinity over infinity indeterminate form. Okay, do it again. Will this ever stop? Yeah. Ain't nothing going to change in that denominator. The numerator will eventually reach a constant number, and it happens in the next step. And it won't be infinity over infinity indeterminate form anymore. So we get a limit as x approaches infinity, applying L'Hopital's rule a second time. 2, the derivative of 2x is 2. The derivative of e to the x is e to the x. This, you wouldn't be surprised to learn, is 0. The denominator gets really big when x gets really big, and the limit's 0. But to make it a touch more formal, let's write it as, bring the 2 out front, a limit of e to the negative x. 1 over x, let's write it as e to the negative x. That was dealt with in a previous example. And you know the limit as x approaches infinity of e to the negative x is 0 from that example, or if you'll think about asymptotes of the appropriate exponential function. So we get a limit of 0 out in this one. We've applied L'Hopital's rule twice, and this is an illustration of an infinity over infinity indeterminate form. Okay, let's formally define some of these other indeterminate forms. Limit as x approaches a of f of x minus g of x is, I'm not doing arithmetic, I'm defining symbols, infinity minus infinity indeterminate form if the f of x and the g of x both have limits of infinity. Bad question. Well, what is infinity minus infinity? Don't make me hit my head again. You don't do that. What infinity minus infinity is an indeterminate form of a limit. It's not an arithmetic statement. If we've got a product and one of these has a limit of 0 and the other has a limit of infinity, it's called a 0 over 0. I'm sorry, 0 times infinity indeterminate form. And we saw an example of that in this previous exercise. What really is 0 times infinity? Well, you don't do that. We went through this. It's 0 times infinity is a type of indeterminate form of a limit. So what's the infinity symbol to you in Calculus 1? It's a limit. When you see it combined with other things like this, it's describing the indeterminate form of a limit. Limits can be infinite, and limits can have indeterminate forms involving the infinity symbol. But it's been very specifically stated, we've never divided by 0, we've never done arithmetic with infinity. You can't. I mean, that's the reason these things are called indeterminate forms. The limit could take on any value. We got an infinity minus infinity indeterminate form, could be 0, could be infinity, could be negative infinity, could be 7, could be 1, could be undefined. That's why they're indeterminate forms. Knowing that they're of, say, of an infinity minus infinity type doesn't tell you what the value is. It tells you the type of limit you're dealing with. And maybe you can use L'Hopital's rule. L'Hopital's rule can be used on 0 times infinity indeterminate forms using reciprocals. That's what we just did. And 0 times infinity. I want to write these as quotients, right? So the point is to get a quotient. We could get a 0 over 0 indeterminate form, or an infinity over infinity indeterminate form. The one we just did, we put the exponential function in the bottom. If we'd have kept it in the top and put the, what was it, an x squared term, put that in the denominator, we would have had infinity over infinity. And we would have gotten similar type results. So just some examples. This is largely a mechanical section. So working problems. Here's a quotient. It's got log functions in it. I don't care much for these weird log base 2, log base 3 logarithms, but man, they're part of calculus 1, so what are you going to do? Evaluate the limit as x approaches infinity of this quotient of log functions. Okay, we'll call f the numerator function, log base 2 of x, g the denominator function, log base 3 of x plus 3. Those log functions, as x goes to infinity, both of those log functions go to infinity. So we do indeed have an infinity over infinity indeterminate form here. Log functions, when you put big values in, give big values out. They do it awfully slowly. Log functions grow agonizingly slowly, but they do have these limit properties. Okay, into infinity over infinity indeterminate form. Excellent. So if we want to take the limit of this quotient, let's use L'Hopital's rule. You checked the hypotheses of L'Hopital's rule, didn't you? Yeah, and that's how we knew it was infinity over infinity. Why are these two limits equal to each other? Because I'm using L'Hopital's rule. How can you tell? Because I put the indeterminate form right there over the equal sign. Again, two reasons for doing this. Make sure you're applying L'Hopital's rule when you actually can apply L'Hopital's rule, when you have a limit of a proper, appropriate indeterminate form. And secondly, to communicate the fact that you've used L'Hopital's rule. Because this function and this function, they ain't the same, but their limits are the same. How do you keep track that this is correct? You indicate right there, you use L'Hopital's rule. In the numerator, we should have the derivative of log base 2 of x. To differentiate a log function, you get 1 over the natural log of the base, and then you treat it as a natural log function. So you get a 1 over x. Log base 3 of something, 1 over the natural log of 3, times 1 over the something, times by the chain rule the derivative of the stuff inside. It's just 1, so I'm going to leave it off in this case. So differentiating the numerator and differentiating the denominator, again, not using the quotient rule, using what you're told to use in L'Hopital's rule. So we produce this compound fraction. Let's clean that up. We've got a 1 over log 3, so that'll pop out in the numerator. The log 2 will be in the denominator. We got a compound fraction here. Let's take this x plus 3 up top and the x to the bottom, and it produces, algebraically simplifying, it produces that quantity. All right, what happens now when x approaches infinity? Numerator and denominator still go to infinity. They're just first degree polynomials, and I bet you know what they do. Well, let's apply L'Hopital's rule, though we do have other equipment to deal with this limit. Back in section 2.6, we attack this limit as x approaches infinity of a rational function by dividing numerator and denominator by the highest power of x in the denominator. Remember that stuff? Well, that still works. Let's apply L'Hopital's rule because it's infinity over infinity indeterminate form, and that's a little bit easier. The derivative of x plus 3 is 1. The derivative of x is 1. So that limit is 1, and then we've got this log, natural log of 3 divided by the natural log of 2 as a coefficient. So that must be the value of the limit. Can you simplify this? No. It's a quotient of logs. If it was a log of a quotient, we could write it a different way, but it's not. It's a quotient of logs, and you're stuck with this form. This doesn't simplify. Let's see, we wanted to do, was that number 32? Yeah, let's do another one. Okay, use L'Hopital's rule on this with your, indeterminate form notation. Okay, It's a difference. All right, I want to see quotients, so we might have to do something about that. Let's define f of x to be the first function and g of x to be the second function. 1 over sine, same as a cosecant function. X approaches 0 from the positive side, 3x plus 1 divided by x. That goes to positive infinity. Dr. Bob's infinite limits theorem and some exploration of a sine diagram, is what I was calling it, to see indeed that it does go to positive infinity. Yeah, the numerator, when x approaches 0 from the positive side, the numerator is close to 1, which is positive. The denominator is close to 0, but it's positive. So that's why we get a positive infinity out. And the limit as x approaches 0 from the positive side of the cosecant function. It's got an asymptote at 0. Check out the graph of the cosecant function to convince yourself of that. So I'm taking advantage of previously known properties of trig functions. So, we got infinity from this limit and that limit. We have an infinity minus infinity indeterminate form. What you going to do with that? Change it into one of the two forms, 0 over 0 or infinity over infinity, one of the two indeterminate forms that I do know how to deal with L'Hopital's rule. Okay, so I need a quotient, is what it amounts to. Well, let's get a common denominator. That'll give a quotient, and then we'll go to town with L'Hopital's rule. Okay, so least common denominator would be the product of the two denominators. So I need to multiply this by sine x over sine x. I need to multiply this one by x over x. That'll give us the x sine x in both cases. Get the common denominator, do the arithmetic, take the difference. So we get 3x plus 1 times sine x minus x in the numerator, x sine x in the denominator. Okay, a little space there. So here's what we get when getting a common denominator. We're taking a limit as x approaches 0. And what's up? Denominator, big time goes to 0. Numerator goes to sine of 0 is 0. And that'll be 0. It's 0 over 0 indeterminate form. Okay, so let's apply L'Hopital's rule. I've indicated that I've checked the indeterminate form condition and that we're using L'Hopital's rule. Okay, so derivative of the numerator and derivative of the denominator. Not a quotient rule. Looks like I have to use a product rule in the numerator here and in the denominator here. So product rule to find the derivative of this. Derivative of the first is 3 times the second, sine x, plus the first, 3x plus 1, times the derivative of sine, which is cosine, derivative of the second. Right there you see my little square bracket picture of derivatives. From that we'll subtract the derivative of x, which is 1. So there's a derivative of the numerator. Denominator is a product rule as well. Derivative of x is 1 times sine x plus x times the derivative of sine x, which is cosine x, produces this. Okay, let's simplify that a little bit. So here's where we left off on the last slide. So let's clean it up. We've got a 3 sine x, 3x plus 1 cosine x minus 1. I guess there's not much to clean up there. Not much to clean up in the bottom either. So get rid of the square brackets. They've served their purpose. And we get this limit. Okay, can you plug in 0? You get 0 in the denominator, so you can't plug in 0. What happens in the numerator? Let's see, sine of 0 is 0. Cosine of 0 is 1. This will be 3 times 0 plus 1. This will be 1 times 1 minus 1. You know what? You get 0 in the numerator as well. So this is of a 0 over 0 indeterminate form. All right, let's apply L'Hopital's rule. Are you scared yet? A little bit. With all these trig functions, this could go on forever, potentially. It doesn't. I know if I have polynomials, I know what's going to happen. You differentiate a polynomial enough times and it'll go down to a constant. Yeah, with the trig functions though, I don't know, it could just keep producing zeros. Let's see what happens. It's in the section on L'Hopital's rules. I doubt it goes on forever. So we'll need the derivative of the numerator. Derivative of 3 sine x is 3 cosine x. Product rule again. Okay, here's the product rule again applied to this. Derivative of the -1 is just 0, so it's gone. There's the product rule. In the denominator, derivative of sine is cosine. Product rule on x cosine x. Let me not bore you with that too much. It's a product rule, ain't it? Yeah, I see the square brackets. So trust me, pause the video and double check me. So there's what I get for derivatives. Can you clean this up? Yeah, a little bit. There's a 3 cosine x and another 3 cosine x, so that'll give us 6 cosine x. Bring the negative out front, and that's about it. Minus 3x plus 1 times sine x. Yeah, minus 3x plus 1 sine x. In the denominator, cosine x plus another cosine x. For 2 cosine x's, bring the negative out front. We'll have minus x sine x. Can you plug the 0 in now? Let's check the denominator. We'd get 2 cosine 0 minus 0 sine 0. Cosine of 0 is 1. So we get 2 in the denominator. So yeah, we can plug in now, unless something really weird happens in the numerator, and it won't. It's just a polynomial mixed together with some trig functions. Substitute 0 in the numerator. Who really justifies this? Well, the quotient rule of limits from way back when in early chapter 2, and the fact that these are all continuous functions justify the substitution, and nothing goes wrong. You don't get division by 0 like you would have if you tried this earlier. So we get 6 times cosine of 0 is 1, sine of 0 is 0, so both of those are gone. Yeah, we get 6 over 2, and that limits 3. I don't think you can just eyeball these and tell. I got no insight to give you to look back and say, oh yeah, 3, that makes perfect sense. I see a 3 there, but I don't see directly how that relates to the value of the limit. It was pretty involved stuff, it turns out. So these are not the kinds that you can often just look at and tell what the limit is. You got to crank through all this L'Hopital's rule stuff. Don't forget to check your hypotheses of L'Hopital's rule test-wise. That'll be part of the instructions to help you along with that idea. You like those indeterminate forms? Let's do some stuff with exponential functions. Suppose we have a function raised to a function power. We've seen some of this before. We saw it when we did logarithmic differentiation back sometime in probably the previous chapter, in chapter 3. What you did was you took a logarithm. All right, so, well, here's a rule of thumb. Whenever you see a function raised to a function power, in other words, you got x's in the base and you got x's in the exponent, I'm pretty sure you're going to be taking a logarithm, because you don't really know how to deal with functions in the base and functions in the logarithm in the exponent. When you take a logarithm, that'll change into a product, and you do know a lot of stuff about products. So rule of thumb, I don't know what you're doing, but if you're doing it in calculus and you see x is in the base and x is in the exponent, I recommend taking a log. Here we're considering a limit as x approaches a of f of x to the g of x power. This is said to be of the 1 to the infinity indeterminate form if the limit of the base function is 1 and the limit of the function in the exponent is infinity. By the way, what is 1 to the infinity power? It's an indeterminate form of a limit. Don't give me no number stuff. Don't tell me it's 1. It's not. You don't do arithmetic with the infinity symbol. 1 to the infinity is an indeterminate form of a particular kind of limit. If we had both the f function and the g function having limits of 0, this would be said to be of the 0 to the 0 indeterminate form. What is 0 to the 0? Well, that's another one of them forbidden algebraic manipulations. Anything to the 0 power is the thing divided by itself, and you can't divide by 0. So that's why this is not a legitimate algebraic manipulation. At least it doesn't involve the infinity symbol, but it's like 0 over 0. That's not an arithmetic thing either. 0 to the 0 is an indeterminate form of a particular kind of limit. If the f function goes to infinity and the exponent function goes to 0, it's an infinity to the 0 indeterminate form. All right, so there's your bunch more indeterminate forms. As we'll see, you're going to work them all using logarithms. In fact, theorem 4.5.b justifies that. If the limit as x approaches a of the natural log of f of x equals L, then the limit as x approaches a of f of x, that is, the limit as x approaches a of e to the natural log of f of x, that is the same as f of x itself because the exponential and the log function, those cancel, is the same as e to the limit as x approaches a of the natural log of f of x, and we just hypothesize that to be L, so we get out e to the L. All right, we'll go through proof of it, but the thing to observe is, you see here, the limit's outside the exponential function. You see there, the limit's inside the exponential function. Well, who let that happen? Can you just take limits in and out of exponential functions? What kind of functions can you take limits in and out of? Continuous functions. That was the definition of a continuous function. We had the test for continuity, which boiled down to you can take limits in and out of continuous functions. Yeah, the exponential function's continuous everywhere. So that's what would justify taking that limit inside. In a passing comment, the a value could be finite or infinite. So this is a valid computation under the hypotheses that that limit exists. This is valid even if a equals infinity or negative infinity. Let's go through a proof of that. Okay, and I guarantee you continuity is going to play a role. All right, so the hypotheses were the limit as x approaches a of the natural log of f of x equals L if that occurs was the claim. All right, by the definition of limit, natural log of f of x is defined on some open interval containing I containing point A except possibly at A itself. By saying the limit exists, you're saying that. Remember, very early chapter 2 stuff, definition of limit, formal definition of limit. Natural log is an inverse function of the natural exponential function. We did inverse functions at the end of chapter 1. That's when we introduced log functions, I think. So e to the natural log of f of x, that's the same as f of x. The exponential and the log, they're inverses of each other. I often say it's like they cancel. It's not cancellation in the usual division sense. It's cancellation in the sense of a function and its inverse. Whatever the log function does, the exponential function undoes. They're inverse functions. So that's why we get that relationship there, the very definition of inverse function. And we observed upstairs and things holding. This holds for all I except possibly at A. I don't know the f of a is actually defined. All I know is this limit is defined. So natural exponential function is a continuous function. It's continuous everywhere. Whatever L is, it's continuous there. L's hypothesized to be some particular real number. So when we write the limit as x approaches a of f of x, let's take that f of x we got right here and replace it with this representation. So we just written it in a different form. E to the natural log of f of x is f of x. Hey, that's an exponential function. I can take the limit inside because it's a continuous function. There's where the continuity is used, getting from here to here. Told you so. There'd be a continuity application. The very definition of continuity says you can take limits inside that function. What is the limit as x approaches a of the natural log of f of x? We were told it's L. So I just replaced that with L. So we got a substitution, a definition of continuity, and another substitution. And that justifies the claim. All right. This previous result, it holds for one-sided limits. It holds when a might be infinity or negative infinity. It's this previous result that lets us deal with these kind of indeterminate forms. So let's do 3 examples illustrating that. Notice each of these indeterminate forms has a base a quote unquote base and a quote unquote exponent. Okay, I don't want to be thinking of infinity as a base or an exponent, so that's why my paranoid use of quotes, air quotes, if you will. So we'll be using this previous result that involved, yeah, told you it's going to involve some logarithm stuff. So let's illustrate those with the following 3 exercises. 52 says evaluate the limit as x approaches 1 from the positive side of x to the 1 over x minus 1. Use the notation that we've agreed to use for L'Hopital's rule. Okay. If you plugged in 1, you can't. If you did, you get 1 in the base. You get division by 0 in the numerator. I'm sorry, in the exponent. That's why you can't plug in 1. But I bet you the limit of that exponent is infinity. This is a 1 to the infinity indeterminate form. More specifically, take f of x to be the base and g of x to be the exponent. Of course, the limit as x approaches 1 from the positive side of x itself is just 1. And the limit as x approaches 1 from the positive side of this thing is positive infinity. Why is that? Dr. Bob's infinite limits theorem tells you it's positive or negative infinity. And then you make a sign diagram. You discover the numerator is positive for these x values, close to 1 and a little bit bigger than 1. Subtract 1, there's a little positive amount left. Numerator and denominator for these kinds of x values are both positive. Quotient's positive, limit's positive infinity. So you do it in steps. First, know the limit is plus or minus infinity by Dr. Bob's infinite limits theorem. Secondly, I figure out which it is, positive or negative, by doing sign tests, SIGN sign tests, not trig sign. We've done plenty of those in the past. So anyhow, we get a limit of 1 for the base, infinity for the exponent. So this is a 1 to the infinity indeterminate form. All right, let's take a logarithm. To convert it into something we can use L'Hopital's rule on. L'Hopital's rule is only good for 0 over 0 or infinity over infinity directly. Now this we can turn into something like that. So that's the plan. All right, limit as x approaches 1 of, let's take the logarithm of this quantity. We'll use theorem 4.5b to use this information. So we're taking the limit of a log of this. Why would you take a logarithm of this? Because then I can take that exponent and bring it out front as a coefficient, property of logarithms. Now we've got a product. No, wait, we've got a quotient. So you'll always take a logarithm when you have variables in the base and variables in the exponent. This one melts in your mouth, not in your hands, like M&Ms. But dude, it just became, when we took a logarithm, it became a quotient. And fingers crossed, that's an infinity over infinity or 0 over 0 indeterminate form. X approaches 1. What's the log of 1? 0. X approaches 1. X minus 1 approaches 0. So numerator and denominator do indeed have limits both of 0. Okay, let's choose L'Hopital's rule. We need the derivative of log x. That's 1 over x. We need the derivative of x minus 1. That's just 1. As x approaches 1, can you substitute in? Yeah, it's a rational function, if you like. And we don't get division by 0. Substitute in, we get 1 out. The substitution is justified because we're dealing with ultimately a rational function that doesn't give 0 in the denominator. So the answer is 1. No, we changed the question. We changed the question from x to the 1 divided by x minus 1 to the function natural log of x to the 1 divided by x minus 1. So we changed the function. We found the limit not of the original function, but the limit of the logarithm of the original function. Why, that's where theorem 4.5.b comes in. We know the limit as x approaches 1 from the positive side of this function is e to the limit as x approaches 1 to the positive side of the natural log of this function. This is exactly what that theorem said with f of x and g of x as given upstairs. So we need to exponentiate. We found the limit of the log. Well, you need to exponentiate that to find the limit itself. The limit of the log was 1. That becomes the exponent. We get e to the 1 out as the limit. Maybe that's more educational there. We get e to the 1 out, and the 1 came from the limit of the logarithm. Whenever you have variables in the base and the exponent, you have to take a logarithm because you can't do anything else. And that changes the question. Yeah, it changes it into one you know how to do. So you do that modified question, and then you use the answer to the modified question to answer the original question, which is probably going to involve getting rid of that logarithm using an exponential function. So that's where the e came from. Let's do another one. How about this one? Limit as x approaches 0, e to the x plus x to the 1 over x power. All right, f of x is the base, g of x is the exponent. You got x's in the base and the exponent. We'll be taking a logarithm. Let's talk indeterminate forms. As x approaches 0, this approaches e to the 0 plus 0. It's 1. So the base has a limit of 1. G of x equals 1 over x. Now, I can't talk about the limit as x approaches 0 of that. I need to know the sign. So we need to break this into a one-sided limit. The limit as x approaches 0 from the positive side of g of x of 1 over x is positive infinity. If I take the limit as x approaches 0 from the negative side, then we get out a limit of negative infinity. So it's not entirely symmetric. It's not symmetric at all. But both of these are of a 1 to the infinity indeterminate form. I'm going to evaluate them separately because in one case we get a positive infinity, and in the other case we get a negative infinity. So let's deal with those separately. Their behaviors will be very similar though. So we'll take a limit as x approaches 0 from the positive side of the original function. All right. Let's take a natural log, as I told you to, and we'll be able to use Theorem 4.5.b to take this limit, which apparently is 2, and evaluate the limit of the original function. I'm changing the original function by taking a logarithm of it. Changes the question, but you don't know how to evaluate limits of 1 to the infinities without doing this. So we'll take a logarithm. That changes the question, so we'll have to keep an eye on that. We won't be done at the end of this slide. Hey, you can bring that exponent out front. Property of logarithms. Introduces a quotient all on its own. Okay, awesome. I like quotients because L'Hopital's rule tells me what to do with quotients. In limits of the appropriate indeterminate form, x goes to 0, denominator goes to 0. Excellent. X goes to 0, numerator goes to the log of e to the 0 plus 0. It's a log of 1. That's 0 as well. It really is a 0 over 0 indeterminate form. Apply L'Hopital's rule by differentiating. Derivative of the log of something is 1 over the something. Chain rule, so I should have a little arrow there. Chain rule spits out this e to the x plus 1. Differentiating the log function, 1 over the stuff inside times the derivative of the stuff inside. Derivative of the denominator, piece of cake, and just 1. Let's get rid of this compound fraction and write it like this. X approaches 0. You got any division by 0? Not now. Nice continuous function. We can plug 0 in. That justifies the substitution. And in this case, we get out e to the 0 plus 1. That's a 1 plus 1 over 1 plus 0. Yeah. So we get out 2. So the limit's 2, right? No, not yet. The limit here is 2, but that's not what you were asked. This is not the limit of the original function. This is the limit of the logarithm of the original function. All right, here comes Theorem 4.5b that says, okay, so we need to exponentiate. So I take this limit, I take the limit of the log as an exponent in an exponential function. We just saw the limit of the log was 2, so we get e squared out. So the 2 from the previous slide becomes an exponent on an e, and it's Theorem 4.5.b that puts it there. All right, that was a one-sided limit. Guess what? You do the limit from the other side, it behaves the same way. So let me not go through that. It's repetitious with what we just did. We also get an e squared there. So anyhow, the left and right hand limits of the function are both e squared. Well, if the left and right hand limits are the same, then the two-sided limit is that common value. It's theorem 2.6 for the record. And so the two-sided limit must be e squared as well. So that was a little bit trickier because of the positive infinity, negative infinity stuff. I just take it as one-sided limits, and it turns out they behave in the same way. So we started with variables in the base and the exponent. We had to take logarithms. They changed the form of the function and allowed us to use L'Hopital's rule. Okay, how about this one? So this is a different kind of indeterminate form. Limit as x approaches infinity of x minus the square root of x squared plus x. Use L'Hopital's rule stuff. They've given us a little hint. Maybe I'll make a quick observation about this. If you think you evaluate limits by just plugging in, I can't believe you made it this far. They're way more complicated than that. And it wouldn't make any sense to plug infinity in here anyhow, because you can't do arithmetic with infinity. We can look at limits, which is what this is, of pieces of this. In fact, let's do that. I think this is an infinity minus infinity indeterminate form. You're not plugging the infinity in, you're analyzing some limits as x approaches infinity of some of the parts. And you sure as hell ain't doing infinity minus infinity and getting a number out of that. That's not what we're doing. That's not the concept. Their little hint, as we've often seen when we deal with limits with square roots in them, is to multiply by the conjugate divided by itself. Then we're multiplying by 1, but it will introduce some useful algebra. It'll also introduce a quotient, which is a useful thing with L'Hopital's rule. Okay, so this first piece here, the limit as x approaches infinity of x, that goes to infinity. How about the square root piece over there? Limit as x approaches infinity of x squared plus x square root of goes to infinity as well. That could possibly use a little bit of justification, but I think it should be clear. I can make this as big as I want by making x sufficiently large. In fact, this is greater than the absolute value of x. Were we going in the negative direction, I could probably make some similar argument. Things might change over here. But the first piece goes to infinity, the second piece goes to infinity, and they're subtracted. Then this is an example of an infinity minus infinity indeterminate form. What is infinity minus infinity? It's the indeterminate form of a limit. It's not arithmetic. That's not what the minus symbol means between those two infinity symbols. It's a description of a type of limit. And this is one of them. All right, well, let's follow the hint and see what happens. So we'll take the given limit, we'll multiply by this thing over itself. When you do that, hey, look, this is kind of the form a minus b times a plus b. So when we FOIL it out, the center terms cancel, and we'll get the first term squared minus the second term squared. Okay, that'll get rid of the square root. The denominator gets introduced. But that's not a bad thing, because I want a denominator, so I can use L'Hopital's rule. The numerator simplifies. We've got x squared minus square root squared will just produce this, x squared plus x. The x squareds will cancel, leaving you just with a negative x in the numerator. And we pick this up in the denominator. We did that because they told us to. And we've got a fair amount of experience with these kind of limits. Here's where we left off on the previous slide. Okay, x goes to infinity, then negative x goes to plus or minus infinity. The denominator, x plus square root of x squared plus x is big, that gets big, that goes to infinity as well. This is of an infinity over infinity indeterminate form. Okay, so let's apply L'Hopital's rule. All right, derivative of numerator, derivative of negative x is negative 1. Derivative of denominator, derivative of x is 1. Let's write this as x squared plus x to the 1/2 power. Okay, that'll require us to bring the exponent of 1/2 down, subtract 1 from the exponent. The chain rule's been used here. Don't quite have room for the little arrow, but it's a chain rule that's been used there. Derivative of the stuff inside, the x squared plus x, as its derivative, 2x plus 1. And geez, let's clean that up a little bit. 2x plus 1, let's put that in a numerator. This x squared plus x to the negative 1/2. So let's move that to a little denominator here with a square root on it. And let the 2 go along with it. Algebraically, this becomes this. All right, limit as x goes to infinity. What's the numerator do? Oh, it's just negative 1. So we can't L'Hopital again because we got negative 1 in the numerator. We got something complicated in the denominator. I'm going to step aside and work this individually. I claim this stuff goes to 1. We'll show it in a second. But this piece here goes to 1. And we've got a limit of negative 1 in the numerator and a limit of 2 in the denominator. The limit is negative 1/2, but I owe you details. All right, what happened to this? 2x plus 1 divided by 2 square root of x squared plus x stuff. What happened there? You know, that's of an infinity over infinity indeterminate form. You could apply L'Hopital's rule. It'll behave similar to what we had up here. The numbers are slightly different, but there'll be, bring the exponent down, subtract 1 from the exponent. There'll be a chain rule piece come in there. If you apply L'Hopital's rule to this, which you are perfectly justified in doing because it's an infinity over infinity indeterminate form, you'll get back something that looks a lot like this. I think it'll have the denominator, I think it'll be cubed. I can't see the big picture that well, but you'll have something similar to this. The square root will probably become a square root cubed, I think. It'll still be infinity over infinity indeterminate form. Well, you apply L'Hopital's rule again. Then you get something else that look a little bit like this. This would yield an example of one where it never stops. You keep differentiating with L'Hopital's rule, you'll just keep getting something else of the infinity over infinity indeterminate form. So you're stuck. Well, let's do this one the way we did some other limits involving x approaching infinity. Let's multiply by 1 over the highest power of x in the denominator, or the highest effective power of x in the denominator. I claim that's x to the first power. Think when x is really big, x squared dominates. When you add x to it, you don't get much more than x squared. And when you take a square root, you roughly get x back. Okay, it's a little bigger than x, but you roughly get x back. This term here, when x is really big, is about the same size as x itself. That is x to the first power. So I say divide numerator and denominator by x to the first power. Let's check it out and make sure that's legitimate and works. All right, 1 over x, 1 over x. So we've multiplied by 1. We haven't changed anything. Let's distribute. We get 2x plus 1 divided by x. We get this stuff here divided by x. Let's write that x as the square root of x squared. Granted, that's the absolute value of x, but x is positive. It approaches positive infinity. Now, distribute the x's inside. We'll have 2x divided by x, which is 2. We'll have 1 divided by x, which is 1 over x. So here's your numerator. And we'll take this x squared, square root of, distribute that in the denominator under the radical. We'll have x squared divided by x squared, which is 1. And we'll have x divided by x squared, which is 1 over x. Make sure you convince yourself that these are legitimate algebraic manipulations. All right, limit as x approaches infinity. We've done many of these in the past. The 1 over x terms are going to go to 0. I can take the limit of the quotient, and I can use sum rules, and I can use root rules, and all that stuff. Constant multiple rules will be needed. This can be justified, and we'll get zeros out for the 1 over x. So indeed, the limit of this thing here, it is 1. And that's the substitution we made from here to here. I just stepped aside and computed it separately. So there's an example of an infinity minus infinity indeterminate form. I could come up with other infinity minus infinity indeterminate forms that don't give negative 1/2. Yeah, that's right. because they're indeterminate forms. They could be anything, including undefined. Oops, I think this is another topic. So let's see. Next is Cauchy's mean value theorem, which states the following. We need this to to establish L'Hopital's rule. Theorem 4.7 says, suppose f and g are continuous on the closed and bounded interval from a to b and differentiable throughout the open interval from a to b. Suppose g prime of x is non-zero throughout a, b. The claim is there exists a number c in the open interval from a to b where f prime of c over g prime of c equals f of b minus f of a over g of b minus g of a. All right, first off, that reminds you of at least a little bit of the regular old mean value theorem. Mean value theorem said, forget all the g stuff, said there was a point under all these hypotheses, there was a point c such that f prime of c equals f of b minus f of a divided by, which was divided by b minus a. Said the instantaneous rate of change equals the average rate of change. All right. You know, if we were to apply the mean value theorem to f and to g, I think we get some cancellation on the b minus a's, and that would produce this. So this, in light of the regular old mean value theorem, this isn't that outrageous a claim. Why you want to do this? Well, we need this quotient stuff to go through and establish the proof of L'Hopital's rule. After that, we're done. Yeah, after that, we're done. So let's go through and establish this, and then we'll prove L'Hopital's rule. Okay, so we're looking for a point C where this equation is established. All right, first off, the mean value theorem required that a function be continuous on the closed interval and differentiable on the open interval. Well, f and g are both that. That's part of the hypothesis, so f and g satisfy the hypotheses of the mean value theorem. We can apply the mean value theorem to both of those. G of A and G of B are different because if they were the same, then applying the mean value theorem to G, we would have the existence of a point C somewhere in the open interval from A to B, where G prime of C equals G of B minus G of A over B minus A. But if G of A and G of B are the same, that numerator would be 0, and we would have a point C where G prime of C equals 0. But we were told that G prime is never 0 throughout the interval AB, so there can't be such a point C. If there is never such a point C, then G of A and G of B cannot be equal. Our claim that they're different is justified. All right, so really we're taking the mean value theorem, applying it to the G function and the F function, and taking a quotient. This is written up a little more cleanly, but maybe not quite as enlighteningly. All right, so what we're going to do is define a function capital F of x as follows. We're going to take f of x minus f of a minus f of b minus f of a over g of b minus g of a times the quantity g of x minus g of a, because that's what they suggested. Well, this looks familiar. You know, keeping an eye on where we're going. We're going here. So this looks familiar. We need some derivatives in there, I guess. We'll differentiate this here in a sec. Where's the variable? We define this new function, capital F of x. There's the variable. These are all just numbers. Oh, and there's the variable. So on the right-hand side, there's an x there, and there's an x there, and that's it. The rest of it are just some numbers. I don't know what they are exactly, but they're some determined numbers, determined from A and B and lowercase f and lowercase g. So here's a function. Hey, we said f and g were continuous on the closed and bounded interval, A to B. So capital F is continuous on that interval as well. And it's just really, it's a sum of those two, effectively. There's a couple other terms floating around. But it's a sum of those two, and a sum of continuous functions is continuous. F and G were said to be differentiable on the open interval. Okay, so capital F is differentiable on that open interval because all I got to do to differentiate capital F is differentiate the right-hand side. Also, f of A equals f of B equals 0. Let's check that out. Plug in A for x. If I plug in A for x, we'll have f of A minus f of A. That'll be gone. And we'll have g of A minus g of A. So that'll be 0, and that'll be gone as well. Indeed, we get capital F of A is 0 minus 0 is 0. What happens when you plug in x equals B? Capital F of B would be lowercase f of B minus f of A. G of B minus g of A. So if I plug x equals B in there, we'll get g of B minus g of A. Those are different. Observe that up here. There's a g of B minus g of A in the denominator. If x equals B, these two will cancel out. And then you'll have f of B minus f of A minus, parentheses, f of B minus f of A. This having canceled, then that'll give you 0 again. So yeah, when you plug A into capital F, you get out 0. When you plug B into capital F, you get out 0. So clever choice of capital F, I guess. So what's up with capital F? It's continuous on the closed interval, it's differentiable on the open interval, and at A and B, the values are both 0. We can apply Rolle's theorem. It was a special case of the mean value theorem. Rolle's theorem required that at A and B, we get a value of 0, or at least the same value of the function at A and B. That means, by Rolle's theorem, that there's some number C such that f prime of C equals 0. You want to use the mean value theorem, it'll still imply there's some point C such that capital F prime of C equals 0. The function doesn't change values from one endpoint. I mean, be careful with my words. It has the same value at the endpoints of 0. So its net change over that interval is 0. And that's why Rolle's theorem claims a derivative is 0 somewhere in between. The average change equals the instantaneous change. It's a special case of the mean value theorem where the endpoints are both 0. So what is capital F prime? Well, let's peek back at F itself and see what happens when we differentiate it. Let me bounce back to the previous slide and find the formula for capital F. Differentiate, we get a derivative there. We'll pick up a prime there. That's a constant, that's gone. We'll pick up a prime there. Were I to distribute this and get this thing times g of A, that'd be some constant. So that's differentiated away. We'll be left with little f prime of x minus this thing times g prime of x. The other stuff is constants and gets differentiated away. As I said, we get f prime of x minus this stuff times g prime of x. The other stuff was constant and is differentiated away. What was it? We said f prime of c equals 0. Okay, well, let's plug c in, and we get capital F prime of c, then equals lowercase, here it is, lowercase f prime of c, minus this stuff, times g prime of c. And we know Rolle's theorem tells us that f prime of c, which equals this, by the way, also equals 0. Here we got a formula. We can rearrange this formula, take the negative term to the right-hand side, divide both sides by g prime of c. That's not 0, is it? Right, that's why you needed these hypotheses. We're not dividing by 0. And you'll get f prime of c over g prime of c equals this quantity here. I want to relate this to a rate of change, but I can't. It's a quotient of rates of changes is what it is. But that was the claim. So Cauchy's mean value theorem is a generalization of the mean value theorem. If we were to take the g function as the identity function, g of x equals x, this would reduce down to the regular old mean value theorem, it turns out. We did this so we can prove L'Hopital's rule. Theorem 4.6, as we stated it, f of a, g of a are 0, f and g are differentiable on an open interval I containing a. The derivative is non-zero on that interval, except maybe at a. Then we get the limit as x approaches a of f of x over g of x is f prime of a divided by g prime of a. Oh, assuming the limit exists. Okay, so we'll look at one-sided limits. They'll behave quite similarly from both sides. Suppose x approaches a from the positive side, and x is inside this interval we were talking about up there. On that interval, g prime of x is non-zero. That's where the interval came from. So we can use that theorem we just proved, Cauchy's mean value theorem, theorem 4.7, and apply that to these functions on the interval a to x. Instead of applying it on the interval a to b, we're applying it on the interval a to x. Right-hand endpoint's x instead of b. All right, well then that implies there's some number c between a and x such that f prime of c over g prime of c equals f of b minus f of a over g of b minus g of a. I mean f of x and g of x. We're taking the right-hand endpoint not to be b, but to be x. So this is exactly of the form that we just had in that previous result, except we got x as the right-hand endpoint instead of b. All right, so that gives us a relationship involving a quotient of derivatives. You like that? Yeah, I think so. And I want to see something like this. I don't see any limit stuff down here, and these don't have a's in them. But other than that, we're making small steps in the right direction. Okay, f of a and g of a were both hypothesized to be 0. So we can drop those from the conversation. Now we get then that f prime of c over g prime of c equals f of x over g of x. You like that? Yeah. Yeah, here's some derivative stuff. It doesn't have the right thing in it. It's got c in it instead of a. And here's some f of x divided by g of x stuff, like we have over here. Well, it doesn't have a limit in it on the right-hand side, so we're not done, but we're getting warmer. So this looks somewhat like this. Now, this is a bit subtle. As x approaches a from the positive side, so what we're doing is we're taking this x value and squeezing it over towards the a value from the right. So we're taking that kind of limit, right? We're going to look at a one-sided limit as x approaches a. As x approaches a from the positive side, we'll see x approaching a. This little interval will get smaller. I won't take x equals a because I'll do a limit thing. What's up with the c value? C is between a and x. So you want to think of it like this. C is stuck between a and x. X is going to approach a from the right. Well, guess what? Since c is between a and x, as x approaches a from the positive side, c is going to have to approach a from the positive side as well, because it's stuck between a and x. You do not set x equals to a. You do not get c equals to a necessarily. When x approaches a, c has to approach a, because c is stuck between x and a. And all of this is happening on the right-hand side. We'll just flip this interval and have limits from the negative side when we consider the limit from the negative side. So if we take a limit as x approaches a from the positive side, that's equivalent to taking a limit as c approaches a from the positive side because of the relationship between a, x, and c. All right, so let's do that for this. Okay, so we had f of x over g of x equaled f prime of c over g prime of c. Now we're going to let stuff move. We're going to evaluate limits. So if we take a limit as x approaches a of the left-hand side of that equation, that's the same as a limit as c approaches a of the right-hand side of that equation. So c is not a constant. It's moving like a variable. Remember where it is, though. Well, the limit as c approaches a from the positive side is the same as the limit as x approaches a from the positive side. These two approaching yield equivalent constraints on both a and c. Well, we started with this constraint. We've got a constraint on the a parameter, just taking the limit over here. I think I like that argument better. And taking a limit as x approaches a from the positive side, that's going to require c to approach a from the positive side, and we'll plug in these if we can. So the limit will give us what we get by forcing the c value to approach the a value. So this can be written in terms of this. We can substitute in, provided nothing goes wrong. We've checked a one-sided limit. We need to check the other side as well and make sure that what we get out of this actually is f prime of a, g prime of a. Well, it's the same argument. Instead of the interval from a to x, you take the interval from x to a, you get limits from the other side. Then you'll have this one-sided limit equals that one-sided limit, and the other side has the same limit, and that's how we'll produce that the limit of f of x over g of x is f prime of a divided by g prime of a. And that's why we needed Cauchy's mean value theorem to establish L'Hopital's rule. And that's it, right, for this section. And we went through the proof for what it's worth. The book gives a little picture to give you some geometric insight for the reasonableness of Cauchy's mean value theorem, I think. So anyhow, we've established L'Hopital's rule. You like L'Hopital's rule? Yeah, like what I tell you to like. You like L'Hopital's rule because it involves derivatives, and you're good at differentiation. So that makes L'Hopital's rule super useful, but it doesn't apply to everything. It only applies to limits of a 0 over 0 or infinity over infinity indeterminate form. But we just turned a bunch of different stuff into those kinds of indeterminate forms. Infinity minus infinity, we turned it into one of those two indeterminate forms and used L'Hopital's rule. 1 to the infinity indeterminate form, we took some logarithms, as we would when we had variables in a base and an exponent, and turned it into a 0 over 0 or infinity over infinity indeterminate form. You got to have those indeterminate forms to use L'Hopital's rule, 0 over 0 or infinity over infinity. But a lot of stuff can be turned into those forms. Then you can use L'Hopital's rule. You might have changed the function. You'll have to deal with that. It's where the exponentiation came in, for example, with the logarithm stuff that we did. But if you can apply L'Hopital's rule, it's not very hard because it involves differentiation, and you're so good at differentiation. So that'll do. For this section, we have yet another section that's applications of derivatives, and it's a lot of applied problems. Classically fairly difficult, but we'll hit that section next and kind of go back to the ideas of graphing and maxes and mins in the next section. But more applications of derivatives. Have a nice day.